Hello everyone and welcome to our session. I'm Dr. Eris, and today we are going to explore the foundations of the microscopic world. Quantum mechanics often feels like a different universe, but it is actually the underlying logic of our own. To understand it, we must start from the very beginning. As we move beyond classical limits, we realize that the physics of Newton and Maxwell, while excellent for cars and planets, cannot explain the behavior of atoms. At this scale, classical mechanics fails. We need a more fundamental framework to describe the non-intuitive reality of the quantum realm. Take a look at this visual. It represents the transition from the predictable paths of classical objects to the probabilistic nature of quantum particles. This shift requires us to rethink everything we know about measurement and existence. This brings us to the concept of postulates. Think of these as the axioms of physics, the mathematical starting points that we cannot derive from other laws. They are the rules of the game. Today, we will examine the 5 pillars that define quantum reality, providing the mathematical consistency needed to bridge the gap between abstract theory and physical reality. Clara will be helping us navigate the mathematical notations as we go. Let's get started with our first pillar, the state of a system. Building on our overview, let's dive into postulate 1. This is the foundational rule that establishes how we mathematically describe reality at the atomic scale. At the heart of this postulate is the wave function, psi. While a classical particle has a definite position and momentum, a quantum system is described by this vector. As Clara will show us throughout the course, this single mathematical object contains every piece of physical information we can possibly extract from the system. Now, where does this wave function live? It doesn't just float in empty space. It resides in a mathematical environment called Hilbert space. Hilbert space, denoted by this stylized H, is an abstract infinite-dimensional vector space. Think of it as a rigorous playground where all possible states of our system are represented as vectors. The geometry of this space is what allows quantum mechanics to be so mathematically consistent. Finally, because our states are vectors, they follow the principle of superposition. This equation tells us that if 2 states are physically allowed, then any linear combination of them is also a valid state. This is the logic behind why a particle can appear to be and rather than or. It is literally a sum of possibilities until we perform a measurement. Welcome to the quantum world. This visualization shows a particle in an infinite square well. The rotating blue spiral represents the complex-valued wave function, psi. The n slider controls the energy level. In quantum mechanics, energy is quantized, meaning it can only take specific integer values. This is the ground state n equals 1. Notice it has no nodes points where the wave function is 0 inside the boundaries of the well. Toggle the probability density to see the magnitude squared of the wave function. This represents the likelihood of finding the particle at a specific position. Observe that for n equals 3, there are 2 nodes where the probability of finding the particle is exactly 0. The number of nodes is always n1. The phase of the wave function rotates over time. Increase the speed to see how the complex component evolves according to the time-dependent Schrödinger equation. Notice how the wave function must go to 0 at the walls of the well, the boundary conditions, ensuring the particle is trapped inside. Building on our discussion of the wave function as the state of the system, we now need a bridge between that abstract wave and the physical world we actually measure. This brings us to postulate 2, observables and operators. The postulate tells us that every physical observable, any quantity we can measure in a lab, is represented by a linear Hermitian operator. Instead of a simple number, we use a mathematical instruction that acts upon the wave function. Now, why must these operators be Hermitian? As Maya often highlights in our derivations, the math must serve the physics. Hermitian operators have the unique property that their eigenvalues are always real. Since we cannot measure an imaginary position or a complex energy, this property ensures our mathematical framework yields results that make sense in reality. Let's compare the classical variables we know with their quantum counterparts. In the classical world, position and momentum are just variables. In quantum mechanics, they are operations. For position, the operator is quite simple. We just multiply the wave function by the coordinate x. It's the most direct translation from classical to quantum. Momentum, however, is more complex. It involves taking the derivative of the wave function, scaled by Planck's constant and the imaginary unit. This highlights that information about motion is encoded in the shape or the spatial variation of the wave. Think about how this connects back to the boundaries we just covered. Building on what we just covered regarding the relationship between math and the physical world, let's examine postulate 3. This postulate is the bridge between our abstract operators and the actual numbers we record in the laboratory. The measurement rule is strikingly precise. When you measure an observable, you cannot get just any value. The only possible results are the eigenvalues of the operator corresponding to that observable. We see this mathematically in the eigenvalue equation. Here, when the operator A acts on a specific state, it yields a scalar value A, the measurement result times the state itself. This defines the discrete nature of many quantum systems. These preferred states, or eigenstates, are the configurations where the system has a well-defined value for that observable. If the system is in an eigenstate, the measurement outcome is certain. To visualize this, think of the discrete spectral lines of an atom. They represent the unique allowed energy transitions. This links our abstract vectors directly to the needle readings or data points we see in reality. Now, let's consider how this forces us to rethink what a state actually represents before a measurement occurs. Building on the idea of eigenvalues we just covered, we now arrive at postulate 4. This is the crucial bridge between the abstract wave function and the experimental results we actually see in the lab, the Born rule. The Born rule tells us that the probability density, the likelihood of finding a particle at a specific position, is given by the absolute square of the wave function. It's important to remember that the wave function itself isn't a physical thing we can see, it's the squared magnitude that gives us observable probabilities. Think of this as the intensity of the quantum wave at a given point. Where the amplitude is high, you're much more likely to detect the particle. Now, this leads to a very famous and somewhat controversial concept: wave function collapse. Before measurement, the system can exist in a mix of states. However, the very act of measurement forces the system. It jumps from that spread out cloud of possibilities into a specific eigenstate. The randomness of the universe is resolved into a single fact at the moment of interaction. For this to make sense mathematically, we must satisfy the condition of normalization. If we sum up the probability over all possible space, the result must be exactly 1. Simply put, the particle has to exist somewhere in the universe. Ensuring this total probability is 1 is a fundamental requirement for any valid wave function. Without it, the math would no longer represent physical reality. Leo, I see you looking a bit skeptical about this forced collapse. Does this feel like a physical event to you or just a mathematical trick? Welcome. This simulation demonstrates wave function collapse, the process where a quantum system in superposition transitions to a definite eigenstate upon measurement. Adjust the complexity to change how many individual states are mixed into the initial superposition. Let's start with a complexity of 2. This represents a simple superposition of 2 possible outcomes, often called a cat state. The precision parameter determines how localized the resulting eigenvalue will be once the wave function collapses. Click the measurement button to observe the collapse. The system will randomly choose one of the available states based on its probability amplitude. Now, let's look at a high entropy state with 8 possible outcomes and a very high precision collapse. Now that we have explored how measurement causes a sudden change in a system, we must look at how a quantum state behaves when it is left alone. Postulate 5 introduces the principle of time evolution. This is the time-dependent Schrödinger equation. It is the fundamental law of motion in the quantum world, serving a similar role to Newton's second law in classical mechanics. Notice that it is a first-order differential equation in time, which implies that quantum evolution is perfectly deterministic. The key operator here is the Hamiltonian, denoted by h. As we discussed when covering operators on page 4, the Hamiltonian represents the total energy of the system. It acts as the generator of time evolution, dictating exactly how the wave function oscillates and moves. To visualize this, let's observe a Gaussian wave packet. While the probability density might spread out, the way it changes is smooth and continuous. Let's watch the simulation. As you saw, the packet spreads over time, but its evolution follows a precise mathematical path. This sets the stage for our final review of how all these postulates fit together. Now that we've explored the dual nature of quantum change, the smooth evolution and the sudden collapse, let's step back and look at the grand logical architecture we've built throughout this session. These 5 postulates are the bedrock of the microscopic world. As we discussed on page 2, everything begins with postulate 1, the state vector. This mathematical entity, residing in Hilbert space, contains every piece of information allowed by nature about our system. We then interact with that state using Hermitian operators. These represent our physical observables like position or momentum, ensuring that the values we measure are always real numbers. Postulates 3 and 4 connect the abstract math to the laboratory. We've seen that measurement projects the state onto an eigenvector, and the Born rule gives us the precise probability of that outcome. It is the bridge between the wave and the particle. And finally, we have the Schrödinger equation, which dictates how the state evolves deterministically over time when no measurement is taking place. Together, these 5 rules form a logically complete framework. For non-relativistic quantum mechanics, there is nothing else. From these few lines of math, we can derive the stability of matter and the very colors of the stars. Our journey today ends here, but your journey into the quantum world is just beginning. Next, we will apply these postulates to understand the hydrogen atom and the complex chemistry of molecules. Great work today, everyone. I'll leave you with one final thought to ponder.